So again, reaction orders are those exponents in a rate law that indicate how the rate is affected by the concentration of each reactant. They must be experimentally determined, nothing to do with the stoichiometry. We said that a reaction is first order with respect to the reactant if the rate doubles and the concentration doubles. If we triple the concentration and the rate triples, it's first order. Whatever we do to the concentration, if the rate follows directly, it's a first order with respect to that reactant. We notice that a second order reaction, if I double the concentration of a reactant and the rate will quadruple, 2 squared giving us 4, tripling the concentration caused it to go 9 times as fast, 3 squared is 9, still gives us a second order overall, squaring the concentration to find the effective reaction rate. And we said a 0 order, no matter what I do to the concentration, it does not affect the rate of reaction. Therefore, it must not play a key role in the reaction mechanism. The experimentally determined rate law for the following reaction is rate is equal to K, NO squared times H2. Notice the coefficients, they may or may not match. There is a 2 in front of NO, but there's also a 2 in front of the hydrogen, but it's first order. So again, just stressing stoichiometry, nothing to do with the rate law. We would say, with respect to NO, it is second order. With respect to hydrogen, that's first order. And 2 plus 1 would be a third order overall. So reading this, we simply say it's second order with respect to NO, first order with respect to hydrogen, and third order overall for that rate law. Would doubling the concentration of NO have the same effect on the rate as doubling the concentration of hydrogen? If I doubled the concentration of NO and it's a second order, it's going to make the rate go 4 times as fast. But since hydrogen is a first order, if I doubled that, it only would double the rate. No, they would not have the same effect. Doubling nitrogen increases the speed more so than the hydrogen. Since the exponents are different, it would not have the same effect. Exponents are different. Most often when we're determining rate laws, we're given data. And we mentioned how we would change the concentration and run the experiment multiple times to see what's going on in terms of how the concentration affects the overall rate. Given the following equation, hydrogen peroxide plus iodide ion plus hydrogen ion forms products of I3, -1, and a couple of waters. This looks like a redox reaction. We're being asked to determine the rate law. Notice that no data is given for the hydrogen reactant. I have data for peroxide. I have data for iodide, but hydrogen doesn't appear. What we then assume is it's 0 order and it drops out. When we're asked to determine the rate law, think of the skeleton that we know so far. Rate is equal to K, that's our rate law constant, times the concentration of the first reactant, H2O2, raised to some power I don't know yet, times the concentration of iodide, raised to the order of which I don't know yet, times the concentration of hydrogen to the 0 order. That could simply drop out, or you may write it down with the power of 0. How does changing the concentrations affect the rate? If we think about trial 1, trial 2, trial 3, we're trying to find convenient trials that we could hold one reactant constant and see what happens to the rate as we change the other. In other words, if I look at trial 2 to trial 1, iodide is being held constant. It does not change. Therefore, it will not affect the rate. From trial 2 to trial 1, the only variance is the concentration of the H2O2. Therefore, it's the only reactant influencing the rate. Another thing I like to do as I'm considering rates is make sure I notice the power of 10. 2 of them are given to the value of -4. One of them is to a -3. So I've got to be careful if I'm thinking about these numbers. One convenient way might be 6.9 times 10 to the -4, 3.4 times 10 to the -4, and this is 0.14 times 10 to the -4. I could think of this in terms of the, equalizing the power of 10 as I try to decide how that reaction rate is varied. Another thing I do actually is get rid of the powers altogether. I could think of this as 0.69. This is 0.34, moving their decimal place over, and this would remain the same as 1.4. Whatever you need to do to just see it equally in your head. But please note that the decimal place is located in a different way. Alrighty. So think about trial 2 compared to trial 1, or you could think about cutting it in half with 1 to 2. When I think about the change in concentration of H2O2, trial 1 compared to trial 2, well, I notice that when I move up, trial 2 started at 0.05, trial 1 started at 0.1. 5 is exactly half as 10. I'm doubling the concentration. Moving from 5 to 10 is doubling the concentration. What happens to the rate in terms of doubling the concentration of H2O2? How do these two numbers compare? And knowing that it's lab data, it might be close and not spot on. But 34 doubled is 68. I'm noticing that's twice as fast. By thinking about doubling the concentration while holding the other guy constant and seeing that the rate also doubled, doubling 34 gives me 68. That's close enough. I believe this to be a first order with respect to the peroxide. Holding one reactant constant, taking a look at what happens when I manipulate the other. The next one we might want to consider, I want to consider trial 1 to trial 3. Trial 1 to 3 holds H2O2 constant, but doubles the concentration of iodide. I like holding one constant and changing the other. Therefore, the rate is only being influenced by the iodide. If I doubled the concentration from 0.1 to 0.2, consider this about 7 to 14. 7 doubled gives me 14. Doubling the rate of iodide, and again, you could hit this on your calculator, 1.4